Yep, so hello again. So my name is Volker, and yeah, I'm a student at the University of Applied Sciences Mittelhessen. It's in Germany, near in Gießen. One city where it is located is in the middle. And I'm doing my master thesis here at GNU. And I have so far looked at the parallelism in Frege versus the GHC. So I did not write Haskell because they are very similar. You see? And yeah, that's that. Well, what is parallelism? So we can think of parallelism like having a pile of documents. Okay, the animation started. It's not yet good. So we have some work to do, and we have this pile, and yeah, we have a worker, and he grabs every single piece of work and does something with it, and this is sequential working. So, and if we want to go parallel, we want to do this in parallel, and this is one big border to concurrency, you may wonder, because I differentiate between parallelism and concurrency, and concurrency would be some different thing, and I'm mainly talking about parallelism here. So, and in Frege or Haskell, we can normally work sequential. We can take this map. It's the same as in the scene above. So we have the function, this is the worker, and a list of things that are the papers, and something comes out. That's the books in this case. So we have this map, functions, and we work on a list, and we apply the work. We work on every element recursively, as you can see. And working sequentially. So when we go parallel, we want to something else. This is basically a very simple example. This doesn't, as we heard before by Ingo, this does not happen directly because the language is lazy. So it will not fall out of heaven to the ground that we get this work, but the worker will only be active when we want to have this book. So then
so to speak, the worker does not produce books, but delivery papers.
Yes, no,
promises to deliver.
That's not the worker, that's the map. So the map will deliver some promise or generator that will activate the worker, that it takes a piece of work and delivers the book then. So this is because of the laziness. So here's an example, so directly related to this map. If we go to the GHCI, it's the interactive wrapper for the GHC, we can create a map, a list by create a list or a promise from 1 to 10, or a func it's called in Haskell, and we can work. We want to multiply it by 2 every element, and we can apply this to every element, and we get this list, we think. But as it's lazy, GHCI has this, we can inspect this, what happens when we do this, because GHCI has a function called sprint that we can look into what actually is here, what we know about this. So if we execute this, we know x's is the func. This means it's a func. So we don't know which elements are in there yet. So when we want to have the first element, we use the head function in this case. We get the 2 as expected, because 1 times 2 is 2. And when we inspect x's again, we see that we now know that the func was evaluated partially, and we have or this func was evaluated, and we have a 2 followed by some other func. So we know it's a list with the first element a 2. So, and if we evaluate the length, we get 10. And if we then look into x's, we get this list, and we see that not all of them, so Haskell only evaluates what it needs to know. We wanted to know the length. So it looks how many elements are in this list, and it does not, it's not interested in the value. So this is the laziness, it only does what it needs. So we know only about this is a list with 10 elements. Oh, I didn't count, I trust it. And the first element is a 2. So we are in this shell, in the GHCI, we are pulling for information, and we get it, and the GHC or Frege does it the same way. Will work, will evaluate as much as it needs to know, that we can get the result.
I think that's very much for us as human beings a trap, because I intuitively never ever guess if I ask for the length of the field or the 10 back, and I would assume that each and every field is evaluated.
Also here, with this, it's not evaluated, it's just a func. It's like a generator, it will generate, if I pull it, will generate a new value. And
yeah, second line says, what is x is, and answer is, it is something. It's cool, right?
It's also amazing that it unfolds the structure without evaluating.
Yeah.
It's quite cool.
so, but when we take the sum, we need to evaluate every element, and it will add that up. Results in 110, and if we look at this axis, we get the whole list. It's fully evaluated.
Could have asked Google instead.
Sure. But not with all these steps between. Yeah, but in fact, this example is from the book I should mention, Parallel and Concurrent Programming in Haskell. It's the same, from Sam Maurer, yes. It's the same example. So it's a very good introduction to parallelism and concurrency in Haskell. So here is it. We have those generators in sequential order. We have our list generator and our worker generator, and we pull, and we get a book. And if we pull, this generator will use this generator to get the papers, and then it will produce the book for us. So I hope this is. I hope the message arrives. This is, so we need to pull, and then it will get executed. So in parallel, we have a bunch of these animations are a bit of order. We have a bunch of papers, and they are transformed into books in parallel. Each worker will work in parallel in the best way. So. And doing this in Frege, we would use a map, parallel. It's the same function signature. Maybe I should tell something about this. I don't know if this is clear to everyone, this writing of the type. Is it clear?
I don't understand it.
Yeah, I may explain it. So. It's just a function. I should have explained it before. It's just a function that is this map P takes a function and a list and gives us another list. And this function we pass. So that's one way to see this. And this function we pass takes an element of type alpha and returns an element of type beta. And map does apply this function to all the alphas in the first list and produce a list of betas. So, and this is the same as before in the map, so the signature of a parallel map, which will result in a parallel execution of or evaluation of this. This we have seen, is exactly the same. There's no difference. we know, we can see there are no side effects directly involved, and we can just exchange the map with a mappee, and it should result, and it will result in the same, it will result in the same result, the same value in this case.
Maybe one thing to note is the Greek letters are not just ivory tower letters. They can actually be used, or are also given by some tools like the Eclipse plugin. And the arrow is a Unicode character here, and is also allowed in.
Yeah, this is
you
very
can write.
yeah.
You can
This
write.
also
This column, but you can also use the conventional syntax.
It's not just for.
And if you don't have Greek letters on your keyboard, don't worry. You can also use.
Yeah, I proved you can do this by default. So
You can write Fraktur actually.
Yeah.
So,
and
we have to talk about that in a minute.
And this mappee does exactly the same instead of this power as the map before. Because remember, this column was between this fx and this map f of x's. So maybe I can go back, or you believe me. So it's the same, instead that we wrote the list constructor in front, in parentheses, and use a strategy power in this case. So we could exchange this with the identity function, and it would exactly behave like the normal map.
Is parallel a function?
Parallel is a function, yes, that will call, I can just write it on, I think I don't have it on your slides.
Does the both sides of the in parallel.
Yes, okay, so I just can run the power takes this operator, I call it f, and on the left hand side and the right hand side now. And it will so execute f of n and p. I hope this. No need. So we have par-op, which takes a function and two arguments for this function, and it will, this par is another function that will finally call the primitive to put an expression into the fork join pool of Java. So it will, behind the scenes, it will then use the fork join pool. So it's a task that it's created, and par is a function that will get and take an A and B, and it in fact then A and B and will return AB. So it's just a type. I won't write on the definition. It's very short, but I don't want to make a mistake. So par generally takes an A, puts this in as a task into the fork join pool, and then returns B. So this here will execute in parallel with A and B and return f of A and B, but lazy. So nothing will happen yet, as far as I know. I'm not quite sure if this, no, this is not executed directly, so nothing will happen because this expression is a thumb. But when we pull, this slide is not, something is wrong here, but the scheme is relative, still matches the idea. So when we pull the first time, this generators will connect to the talk to the other generator they are connected to, and produce a paper, and we will, and this generator that has asked for it will give us a book but the difference is, we can't see this because the animation is a bit slow. We do not pull for new book, but these generators will just go and fetch new, will pull new things from it. So when we have this list, we had before, and use parop on it, and we make a head of the list, this parop will, because we have put this in parallel execution, will evaluate every element of the list, but we only get the first. So in the example before with Aspirin, we would see that it will evaluate every element.
Can I say one sentence? The par is in principle working like sec in Haskell. That means the left side of the par is in any case, if this par op is executed, this par op is run, it runs at least A. And because A can be a func, and hopefully is a func, it will go away and compute this, and it will update itself. So in the later reference A, then we get just the result. And I think it's is it left associative? I think it's left associative, so that the
maybe I'm not sure if it's left or right.
maybe we can look out. In any case, the last, you are right, the last one like in Sec is still lazy.
Yes,
so,
it's lazy because we don't get the evaluation.
But should it execute? Should it execute? Then it will use the already parallel executed threads, and if they are not yet done, then
but only if we have activated this. So when we get the first element, so the head of the list, then the parallel execution is
triggered.
It's triggered. Yeah, thanks. The parallel execution is triggered. This before, and it will subsequently evaluate every other element in this example.
The idea comes from Haskell is that if you have just one core, then this par should behave, or just one head should behave like Sec.
Yes, in Haskell, this par is just an annotation for you suggest to the runtime environment this can be executed in parallel, but you don't know. So
you don't know either.
Yeah, but in Java, you know when you get the when you because it's in GHC you have those sparks that are not tasks. I try to separate them by name. So in Java you have this for join pool, and Frege uses this and it puts a task into the for join pool and it will be executed. And the reference is held by the for join pool and it will not garbage collected. In GHC you have those sparks, so if you put with par, it's the same, into the scheduler, an expression into the scheduler, and you will never use it, and you will forget about it. So in this list, if we have a long list of 1 million elements, and we execute this this map P in Frege, and we just take the first 100 elements, and you still executing, and we have done our calculation with those 100 elements and forgotten those in our code, but it will still evaluate the list to the end. And in GHC, it will something like a weak reference. You will have when you do the same, the garbage collector will see those unevaluated sparks are still those unrun sparks are still are not used in any other code, but only referenced from the scheduler, and it will garbage collect them. So that's it's kind of they do some kind of how do they call that, speculative parallelism. So because they can forget about it, even if you have evaluated some too much, but not all of it. So.
Still, if you have just one CPU, then
yes,
it will never be parallel.
Yes, it's true. That's true. Yeah.
So it will finally behave like Sec.
Yeah.
So that is the guarantee.
Okay. So what did I do?
Volker, isn't it so if I query for the first element with head,
Yeah.
I think there's still nothing on the parallel, right? I just get the first value executes, and the rest is still pending. Only if I do the sum, then all the cells are, so to speak, evaluated in parallel.
So if you grab the head, you will look into. No, you don't know exactly. Is it?
It's like you showed.
Yes, could be. I don't know exactly. Yes, it's lazy, but when you
ask for it, you still don't have parallelism. You just get the unfolding of the structure.
No, if you ask for the length, then you will evaluate the functorist. Isn't it that way? And
but it still should trigger parallelism.
Yes,
right?
that's a good question.
The map P will do it at once. As we have already said, this is just like this fork join tool thing works. I mean, I can just put something in there that doesn't do anything.
Yes, this was
therefore
you need to get this because you don't know exactly, and you have constructed this with the recursive call, and yeah, you will grab for it, and then he needs to evaluate it because he does not know. He needs to go all this way down, all the cons down, all the list constructors down until the end, until he hits the empty list, and as we are triggering the evaluation of this f of AD in how this here will be also
Yes. It doesn't execute or it's not evaluated when we just call for the length of the list.
but it will be started the execution.
It will be executed.
Yeah.
Sure.
Because this part is or has to be more strict than the ordinary map is. Look, that's what because I said if you have instead of par, if you had sec there, then you would also this would mean that the argument A is a strict one, and also B. So already in the map P, those things would be evaluated.
And to add to the confusion, I would claim it's actually so that as soon as you call map P, right, so that map P must be called. Okay, yeah, for some reason. Because when you have map P could itself be lazy evaluated in the thing. So as soon as it's called, the whole list will get their entries, but these entries are only in VCAT normal form. You know, they are not fully evaluated in a deep sec sense. They are not fully evaluated to an actual value, but it may contain the func. So
yeah, but if you confine ourselves to numbers, for ease of discussion, those numbers will be there.
Yes, exactly.
Already, even if you only do them.
Because otherwise there would be no point in doing it concurrently, you know, because then you would pay the price of evaluation at the later time when you lazy evaluate. But this is not what you want. You want to pay it early, early and concurrently.
In some sense, the goal of parallel execution is exactly opposite to the laziness. In lazy evaluation, you want. You don't want those values created because you maybe need only the hundreds or the 200s, and it's very expensive to compute them. In parallel, you know you will probably use all, and they should learn CPU as fast and compute as fast as possible.
So we can easily verify.
Semantics is in this case the semantics of MapP is strict on the level of the elements, but of course if the elements are themselves lists or something more complex, then you have to take extra measures to evaluate them fully if you do want this. Maybe you don't want this. But up to weak head normal form, that means you know the constructor, and for simple values that means you know the value. It is evaluated right away in the part. In the moment when the result of MapP itself is required. If you write MapP as one side of the left as left element of a tuple, and the right something else, then it will be there, no fork join tool ever created, nothing. And if you then take only the second half of the tuple, then it will go away. It will never do any computation. But if you say what is the left value in this tuple, then it will start executing, running out of it.
But to weak and normal form, it's correct.
Yes.
Yeah. But if that would be if we have the numbers, then the weak and normal form is the number. But when there is something bigger calculation going on, another list maybe, list in the list, and then only the inner lists will only be evaluated to weak and normal form. So you would need to apply other strategies to evaluate them. That is what the evaluation strategies in GHC do. So those give you this tool, these evaluation strategies in GHC give you something where you can compose strategies and use them on data structures and can exactly can describe how you want to evaluate them. So if you also want the inner list to be evaluated to weak and normal form or fully, or
what do you think? Is it easy or hard to add some kind of tool like a debugging tool that helps me to understand the structures in terms of how far are they evaluated? Because that would help very much to get a correct mental understanding of how Haskell or in this case.
You mean in the result? Yeah. Should be fairly easy, I think. Yeah. Is Marvin Mutu already?
Yeah, he's not yet online. No?
But yes, you have to go to Java to do this.
Yeah, there he is.
Okay.
So, Mari Mutu, we have a question for you.
Yeah, you mean something like this
Sprint.
GHCE command? Sprint. Yeah, just ask Marine to implement it. It comes down, because it comes down to going to Java code to check if a func or if something is actually evaluated or not. You cannot see this from Frege itself because it is supposed to be the same on this level. But in Java you can surely see it. And then you just print an underscore if it's not yet evaluated and print the value as usual if it is. Well, it should be not too hard, but of course takes some force.
So Mari Mutu says, "Hey all, I said we have a task for you. We want Sprint for the REPL."
Yeah. Okay.
Let's see what he says. And you would like to have it for educational purposes for your students you say.
Because the hardest thing is to get right mental model in something.
I mean, we could call you S4C.
Yeah, you very easily can do this in JavaFX.
Yeah, really?
Yeah, sure.
I should have.
It is simple. If you have a path, you can do this.
So the title was
So
Frege versus GHC. How do I
Who's faster? Right?
Yeah, who's faster? I have the stopwatch and I look at who's faster. That's it. But that could be inappropriate because the one Frege runs on the JVM and GHC is compiled, and there are different environments where they run on. So we can also look at speedups because this is relative. So if the GHC, if the GHC would be faster as Frege in sequential execution, but the speedup is the same in both. When you execute parallel, this should be no problem. Okay, so that's a relative viewpoint. So, but how do I compare the time? So in Frege, I just say I have this benchmark function, which gets an expression path and gets the start time and the end time. After, in between, we force the evaluation of A. This is really important here because of the laziness. It would not be evaluated here if we would not force it. Not only here, but also here. And this force function is just taken from NF data module of Haskell. It will just implement. It will need A to implement the NF data type class.
Will it do deep
Yes,
evaluation?
it's deep state.
Ah, okay. By the way, the compiler will do it for you in this case, but you should write this as a case.
Yes, in the case, yes. We could write this down to
the compiler
case
put
A.
in this case, the compiler just put shift the let out to the left because the expressions before the let do not reference anything, or it could shift in both sides actually. If it doesn't do it, then it's just because of kind. But
it doesn't do it.
It could change it ever at least, but if you cascade this with a case, then it can't do this because the case itself is then in action. So just
okay,
for the demonstration purpose.
That's good to know. But it worked. So,
yeah.
In the I did a try with Frege 223, so it's in use.
Yeah.
So and then we just return the result and the time it took. Okay, now relative comparison. We have the sequential Haskell, the GHC, and the sequential Frege, and the parallel Frege and the parallel Haskell. And we see that the speedups, if you compare how often this blue line fits into the green line, so you see the speed up. So and you see Frege in this case, as an example, is faster than the GHC, but the speed up of GHC is much better in this example. So that's the relative comparison I also did with the speed up. Okay, now to the benchmarks. So, by the way, in GHC I just take, this is a bit unfair, but not too unfair, I just take the times by running it with runtime system options and printing the stats how long it took. So that's minimal deviation. So the first benchmark is a Sudoku, which is represented as a string. And yeah, everyone knows the Sudoku, how it solves. We want to solve the Sudoku, but not one, but many of them. And we need, for this, we need a solve function, which just takes the string and returns maybe a grid if we found a solution. Right? And we put this, we map over many Sudokus and the solve function and just put this whole line into the benchmark. So we could also use, I put this because I wanted to know if really how many are solvable of them. We could also have taken only map solving puzzles, but here's some sequential. If you go parallel, this will just this length will be a bit strange, but it did not affect it. Because I did it also in Haskell the same way. It will not affect any of the measurements. Also. And when we go parallel, we just use map_p, or in GHC, we use parmap with the strategy as sequential. So because we take the length here and everything is passed into this, this will be executed parallelly. Okay. And those are the results. So we have this benchmark. We have here Frege, and here the GHC results, which are on this on the y-axis is showing the milliseconds it took, and on the x-axis we see the parallelism, which is sequential parallel. So it was a PC with 8 hyperthreads, so it's one CPU, 4 cores, and every core has 2 hyperthreads, I think. So the maximum parallelism is 8. And then GHC side, I have just taken the parallelism option of the runtime system into account because it is possible. And on Frege side, we have just this fork join pool. It takes what it gets. It will be created and everything will be done. And you see also that those are box plots, but they are nearly, so I think 100 runs, everyone. And you see that there are only the minimal amount of outliers, and those are like a line, so it's strange, we can't see really the box. So you can also get a speed up of Frege and GHC a bit, but I will show this on a different slide then. And we see that GHC in this example is much faster than Frege. You can see, so GHC with full parallelism only takes 1 second, and Frege still take full parallelism 3.5 seconds. But now to the relative comparison, what is really interesting then? Yeah?
My question is,
yes?
This solve algorithm, does it use higher order functions much? Or also type class functions?
Well, it's constraint solver, which is, I'm not sure, it's a go.
If you don't know,
so
we can look later.
No, we can talk about this later.
But this would then just be interesting.
Yeah.
Interesting case to compare it. With the new code generation where
that's true. But I don't know if this.
As I think higher order should be faster. The implementation of higher order should be faster.
I don't think so, but I need to look into the code. I don't think I have used it. Order functions. I don't pass functions.
Sometimes you don't see it. You just have maybe.
We can later look into the code then. Okay. So, and the speed ups look much better for Frege than this. This slide. So the speed up in Frege is nearly 3, and in GHC with a maximum parallelism is 2.5. And we see in GHC it is really, the speed up is really, it's not that much, it's not that linear, but we have some, maybe we have some sequential parts in this. Every program has some sequential parts. So.
It is so good to have these measurements, have the benchmarks. It tells you so much. Every time that you do benchmarking, especially in parallel code, you're surprised.
No, really.
You're thinking this is all computational. It can be parallelized almost without any static part in it, unparallelized part. You expect it to be 8 times faster running on 8 cores, but it's only 2.6 or something. It's always interesting to do the measurements.
It's also, first I thought it was really 8 cores, but it's only 4 cores and 2 hyperthreads. So
yeah,
we don't know exactly. So
actually, I did run it on my machine where I can see how much the cores are really doing, and as you see interesting patterns like only every second one is going up, or maybe almost nothing happens. Right? It seems like almost nothing happens sometimes. Like so, interesting. So it's also good to use the system tools then.
But my PC was fully working and
Yeah.
was working
Okay.
coal miner. So, so another data point gathered by the Mandelbrot set calculation. So those are those neat pictures of yeah, maybe you know all of it, but
Mandelbrot,
who doesn't know it? Who does?
Julia said something.
It's just the heavy number cruncher calculation on the complex plane. So we have this complex number within real time and imaginary time, and we have a grid where this is located, so we can draw it on a 2-dimensional grid, which consists of those complex numbers, and we just look into specific, so into a specific range, and with because it's a floating point, we also define a step, how much we which points in this flat plane we are looking at, and the calculation happens in the eta function, which takes a complex point, and as we can calculate, there are some points where it will run forever. We just need to pass it an int for the maximum depth, the maximum iterations you will do, and we get out of it the complex number where it stopped, and the iteration depth he reached, because he will stop calculating at a given point. When the complex number he is calculating diverges into infinity. So this is again passed to map, P, and RMap. So we have the grid and map over it with the iterator for the point. So we look at each point and calculate the eta function and it stops at the maximum or at some point for where we set the breakpoint for this. So again, map P for parallel and Frege, and parmap and dipsec for this in Haskell, GHC. So it's just pure calculation, pure addition and multiplication, and finally we got to those numbers, which are really interesting because Frege in this case is much faster for, I think, 60,000 points calculation. Calculating it took only under 3 seconds, and the fastest GHC version in the highest parallelism is at 5.5 byte. And there comes to play because GHC has also this other backend for compilation, LL4M, and those numbers get a bit lower. So we only did it for the backend for C. And we also see in the sequential part that there are many outliers, and the mean value is not in the box plot.
How do you answer
how many times I did it. So I did the measurements, I did always 100 times. And so you see only this, here you see what's all a bit more spread, so yeah. Looks really strange sometimes. Yeah. But
the ones with two entities, or
with this two threads in the scheduling.
okay.
So this means again. So here we have the milliseconds, Frege part, the GHC part, and the parallelism, which is the sequential, the full sequential 2 cores, 4 cores, 6 cores, 8 cores.
So the 2 cores are
hyperthreads. The 2
so
cores.
you play the VM, or is it?
No, that's actually on this level. Yeah, it's no VM, nothing in between. I unplugged it from the net. I stopped cron, and
we really did our very best in making accurate measurements. But this is anyway a surprising result. I was in the beginning, I thought, well, we are giving back a pair, and maybe it only evaluated to VCAT normal formats, not doing the right thing, and so on. So we validated whether it really evaluates to what it should do, and it does. So
yeah, there's a big story behind, because first it looked really different. So as I wanted to talk about this later, but I can do now because we were using, as you see here on this previous slide, so we are now using this strictly. Before I had used the pair because it's a pair of numbers, so I thought I should use a pair. So on the Haskell side, on the GHC side, it worked perfectly fine. And then we discovered that this took, I don't know, instead of 3 seconds, it were by 20.
like 10 times slower than
10 times slower,
Haskell.
30, 20. And this is because of what Ingo talked before, of the polymorphism in the tuples. And even if you do it strict, it will not work then, because it still has object, and here it creates a double. So, but it's not too different from other. So I haven't optimized it to the. I could have used another algorithm maybe or something, but at this low point, it should, for me, it still should look functional and not too optimized. And this still looks optimized, not so optimized, because you still have this pair of doubles, and in a complex number you only want to have doubles.
Do you use the same data complex for Haskell?
Yes.
Also?
Okay. Yes, I use the same.
Because I noticed that when you ask on Reddit, I noticed that Haskell actually has in its library this data complex A. It's also parameterized. And if you use this one, then Frege had an unfair advantage because we restrict the types to double. But if you
I used it before without this. I used in both the tuple.
you had tuples first, and then
yes, I switched on both sides.
You don't use the internal Haskell complex.
No.
Okay.
So I did the same on both sides. I used before tuples in GHC and in Frege, and after that I use after this discovery.
Then, and since that was so surprising, we then asked on the Reddit, on the Haskell Reddit, for possible scrutinization of this. You know, we have this crazy data point. We'd like to understand the data point. Do you think it's a fair comparison or not? To give the Haskell community a fair way of telling us. Yes, and then it's always like on the internet, you ask for something and you get something else back. So people came up with alternate solutions for how you can calculate Mandelbrot and other problems where, you know, performance comparison would be the other way around. You know, we have all those data points. It was not the question. You know. Anyway, until now, we have not yet received any scrutinization of this where people kind of questioned the data point as such. So At the moment, we take it for granted that it's a valid data point.
Yeah.
And the other one as well. I mean, the other way around. It's, I mean, the typical misinterpretation would be, if I'm allowed to say this, would be you have one data point and you extrapolate that. All my Frege programs will all be a factor 3 faster than the Haskell programs.
But as we showed before, the Doku.
This is why I asked for the solve function of this Sudoku, if it involves a higher order polyformism or higher order functions or something, because I think this Mandelbrot is really, really number crunching. You don't even, you just add things and subtract, and that's it. So you abuse, so to speak, a functional language as kind of FOTA or something. So
fourth, since it's FS, since it's FR.
And I think the by necessity, the Java code that comes out of this is relatively straightforward, I think, and the JVM will be good at optimizing it and will do all these things. But as soon as you have such a new function in it, then things will get difficult, more expensive.
Only use really, I think I don't create some word, maybe in.
I mean, in the inner loop, the inner loop of the Mandelbrot, we know for sure there is no higher order functions or something. That's just going. And I will have to look at this, at the solve. I think I have a well-trained
much better.
I mean, this result is very nice.
Yeah,
but we have to explain why there is such a huge difference compared to the other one. And then I got to work on this point.
And by the way, we don't put it in the official comparison, but since we are between us, you know, and nobody listens, we tried our very So we tried our very best to also compare this against the Java solution. Now, a plain Java, handmade Java solution is, of course, a little bit different since you have the algorithm different.
Yeah.
We tried our very best to make a fair comparison there as well, and still, Frege comes out 2 times faster. It was about 2 times faster in that regard. And so this kind of problem, or this kind of solution to this problem, is like
I think,
particularly nice in Frege. For some reason.
Really
it's a bit of a reason.
But I mean, this is people underestimate. I mean, that's what I said in this Twitter communication, that the just-in-time compiler really loves immutability and purity and all this stuff. And if you have this in a form he can understand, it will do really good code.
But the Java version was with final everywhere.
You had some arrays or something?
I had one array,
and
but I used
updates there, and then you have, you know.
It looked pretty well. I mean, we write Java every day since 25 years.
I believe you. But you think that code looks good. But,
you know. You're surprised. That would not be surprised.
It's always surprising.
The JIT compiler thinks
differently. Anyway, that's also an interesting finding.
I had this effect before, when I had this, I have another benchmark, but it's only marginally. The Frege is only marginally faster, I think 90 or 95%. It's also in the examples where we have this number of p digits.
Number of pi digits.
This is from this computer language shootout. I took this Java version and the Haskell version and somehow. So it can be, in Frege indeed can be faster, but my experience so far is that as soon as you do higher order functions, including type class operations that cannot be resolved at compile time. I mean, when you write 42 plus n, then the compiler knows that this is integer. There will no dictionary be passed and so on. But if you really have to pass a dictionary and run the function through the dictionary, then it's higher order case and it goes slow, much slower.
Yeah, you have an indirection.
So this may be an explanation, but I really would know.
Sudoku. Yeah, the Sudoku was also slower in the beginning because I used the version where they. No, this was this one. It was not the Sudoku.
However, I feel that one gets easily sidetracked by comparing the performance like in absolute values, right? Because we'd like to have some justification for running Frege, of course, right? Anyway, so for the special task of Volker, the task has been different. The task was really, we have some code, and how that relates to Haskell and Java, we don't care. But we would like to have a safe refactoring from sequential code into parallel code and see a speedup. That's more the story.
Okay.
And unfortunately, now it comes, the speedup is a little bit less than in GHC, because even though we are
This is the next slide.
faster
but-
than.
Yeah.
Those
Those are the speedups. So
are the speedups. So
wait a moment. It's taking some time. So now the speedups of Frege. Yeah, it's not that good, but of GHC still 2 in
over 8
the
cores.
So, yeah. That's it. That's a prize for being fast. No speedup. this time. Okay. But also, we were creating with this map. As you remember, we just call the eta function with a map, and we have 60,000 points. And for every point with a map, we create a spark in GHC or a task in Frege. And with the default values of GHC, you see something like this. So we have here the number of sparks. So you can introduce this with thread scope. Here's the time. Here's the number of sparks. So, and just pushing those 60,000 points into the number of sparks, into the result something like this in GHC. So, and I wondered, because the times were different, what happens here? So, the sparks suddenly drop strange, really fast. So, not in a linear way as you would expect. So, and it turns out that on the output, you see that many sparks are dropped because the scheduler is full. So also this number, so you can set it up to 60,000. It would not be that necessary to do this exact number, but and then you see something like more like this. You see some something like this. The time is shorter than because it's faster. But you see a linear. So I should have drawn this. So you need to tweak a bit on the GHC runtime, and Frege you haven't to do this because it will create this for join pool and just take what it gets and puts everything there as long as you have heap. Can create new objects, put it there, and it's still fast. Yeah.
Now this just means that the fork-join implementation is quite good.
It is really good.
Is
It's
there
amazingly good.
Is there some parameter we are setting there or
Nope.
using there?
No, we just set in the Java code. When you create the for join pool, you set it to 2 times of the parallelism of the PC you get from the system's runtime.
Yeah. I mean,
You have to
maybe one. I don't know if it makes sense to vary this number. I just guess
And it is usually interesting to have different numbers for this. We do this in the Groovy GParse project. And for not so much for parallelism, but for concurrency.
No.
For example, you may have only 2 cores, but you're fetching something from the web in parallel, and you want to have 10 threads for doing this, you know. And so it depends whether you're CPO bound or IO bound.
But this for joint pool works better if you give it more than.
Yeah.
It's
So
right.
interestingly, the default in GParse in Groovy is the number of available processors plus 1, not twice the size, but only plus 1, such that when you return something to the pool and fetch the next one, there's always 1 in the pool. And that was the idea. So we have always at least twice as many in the pool actually when we ask. So that is kind of interesting. You know? I found that's an interesting default. Made me think whether GParse would be better with that default.
Yeah, we can try it. I mean, you just take a legacy jar and put this changed thing in there, or you can make it a system property if you want.
Java 8 comes with a common pool, which is the same
Java,
as
you can actually currently set it already with a over a system property as possible. It's kind of a hidden one, but it's possible. Whereas I would rather like to have it like GParse have it with pool, and you run something, and with pool you can give a number, and then you decide the number yourself. I mean, that's...
Yeah, but I think, yeah.
Can we discuss it later?
Yeah, sure.
Sorry. It's a bit deep. It's a deep discussion. So, but before I set this runtime option in Haskell, in GHC, I thought about it, maybe this scheduler in GHC does not handle that much of Sparks, and I did also a blockwise execution in parallel, so I didn't create 60,000 Sparks or tasks, but only a subset. So in 100 blocks, I take 100 points and calculate them in one task, and I did also in and I have not the code, I think. I just watched no, I don't have the code. So I use there are strategies, I think it's called Parabuffer in GHC, where you can pass an integer of maybe 100 or so as block size, and this exists also for lists, so you can use this. And I did also a blockwise calculation in parallel. You see here the results again. So I call it chunk because in Frege there is a function on the list which is called chunk, and you get a chunk list. So in my 100 blocks, a block of 100, and the next block of 100, get a list of lists of the block size. The runtime, the block size for free, for less than 500 block size and above, because we have a slide. The red is the Frege, and GHC is the slightly blue one. And we see that with this block size, it is under the 5 seconds between 0 and 100 block sizes. The execution is faster in GHC. And we see this on the next slide with speedups. And we also notice that if we go up with the block sizes, that Frege performs still better in the speedup than in the overall. So it doesn't really see that it's really scrolling very fast, and it's a bit because IS.
How many data points have you?
That's one. This is again here are 100 points per block. So this one here are 100.
Yeah, but how many?
So
how many blocks do you have?
We have 60,000 divided by 160 blocks.
Okay, so in the last
So
one, we
the
have
last
only
one
6
is
blocks.
it's not that good because we only have 6. Yeah,
Yeah.
I noticed that too, but I did just down through. And we need to look here. Here, I think. These are the 8 blocks. And when you recall the Mandelbrot, it's looking something like you have this structure, and this is this the yeah.
Good.
Maybe, yeah. And you see here those points which are not. It will stop calculating this, and if you have blocks, then if you go up with the block size, then you may have cores that will not do as much as others. So this is the explanation for this. But still here an interesting point. It's really curious.
Nevertheless, I find it's really unexpected that this goes so steep. That's steep. I mean,
yeah, but that's because of those. It will finish at some point, and
then the other perhaps there's nothing to do anymore.
yeah.
Yeah.
It's my explanation for this. In Frege, it's not that bad. Can't be all.
There is what 5,000 to
So
8,000 is 1.5, and you have
So this is
almost the same factor. Yeah, not exactly, but
so I split this because it would be wouldn't look nice if I draw the mean between. So you see that in under 500 or equal to 500 block size, it's nearly the same, and here it really goes up. That's why I chose this. So after 600, it's just those are the speedups for the different block sizes. But no, only those we've seen before, the less than 500, let's say equal to 500, because the are two strange results. Yeah. And we see that this is the best speedup of the parallel Frege, and this is the 8-core speedup of the parallel GHC. And we see with the blockwise or the chunked execution, we get better speedup slightly at Frege, but really half a point better in GHC. So blockwise is better than that. Okay. Yeah. Okay. Now the point where I wanted to write.
Yeah, sorry. I was a bit premature.
No, it's okay. No problem. So we had some unexpected results, as you've seen, and the Mandelbrot version first was in Frege was much slower, so 30 seconds instead of 3 or something. And yeah, we've talked about it because of the tuples, And the Sudoku also, there were I had to implement. I had one version I used was used the arrays of the Haskell standard. So I implemented them in Frege, and this was really bad. What I did first, I used I think it was the Sudoku. Yes, it was the Sudoku. It was much slower. It was 30 seconds instead of was it 10 or so? So it was a factor 3. And then I realized that it could have to do with my implementation of array, and I exchanged it so that it were J arrays. I used J arrays, so Java arrays in Frege, and it wasn't suited for this problem, like in my programming style. And then I switched to the tree map and the hash map of Frege, and the speed went up. So if you consider implementing standard library, then you should choose wisely what to use, and for the problems too. may be appropriate, may have been appropriate for other problems, but for this constraint solver in Sudoku it wasn't appropriate. And as topic says it, the tuples, if you use tuples while number crunching, then you have a problem in Frege. And also in GHC, you have this with the sparks, where you need to, but the output will tell you, the statistics output will tell you that the sparks are dropped when you run it.
Yeah, but the cache map should be really good if you sometimes have to insert or change something,
Yes,
but most of the time.
Because the constraint solver uses fills the Sudoku grid with all possible numbers fit in there. In the beginning, in every field there is, in every cell there is 1 to 9, and then it erases, eliminates the symbols and will create new arrays, and with the hash map it's really fast. The hash map is even faster.
The others have the copying instruction always. Well, because you destroy your caches.
Yes. So if I would just change it in place, then it would be a problem. And it would be possible because I've parallelized it a way where we look at every Sudoku in a single, we take the Sudoku and solve it, and no other guy will look into it. So I just use the parallelization to solve many Sudoku. So if you want to, if you do it another way where you had concurrency, it's another topic. Yeah. So I did gather 2 data points out of many out of there are if you're benchmarking, you get straight results, you need to interpret them, and maybe you are lucky, maybe not. And during the work, we had discussions what to do, how to look at it, and also how far to go into the optimizations. And for me, it was I tried to be to look at the code, so the code should look functional and not too optimized. So you write something down. You can, if you have a map and you think, oh, it's a good calculation. I have a long array, long list of calculations. I can just replace it with a parallel version. Everything is okay. No side effects are happening, and you can just go parallel because everything is immutable. And if you are mutable, you see it because you are in IO mutable. So you are aware of it. And also at the Mandelbrot, we could also, we have thought of, discussed it, where we can have a sort of interrupted parallelism. So if you want to draw this, and so it's a step further to concurrency, you want to look at the Mandelbrot and zoom in, or not even that, you just calculate it, and the user sits in front of the screen and want to see it, and then you have different strategies of evaluation, how deep you go, the iteration level, how long does the user need to wait, where do you interrupt, when you go through the points, do you go each point after another and make a full iteration, or do you start with all points to just 100 iterations instead of 1,000 or something? And it's something like if you walk a tree, every point is a branch of the tree, and you can, how deep do you go? Or how many points do you look at? Is it the depth or the width search you do? Discussed about this, and it's much experience together for me. It's still ongoing, and I see what comes next. Yep.
I have two questions. First one, regarding the strategies in Haskell. What is your opinion? Could we port this to Frege? Or would it make sense to do it? Because you see in the fork joint, we have just power up, and that's it.
Yeah. And so this power up is really a strategy because.
Yeah, maybe we.
Yeah. So this. I know it was on the slide. So this power up is in fact a strategy of applying of traversing functions, of applying functions in parallel. Makes that sense. If you want to use it, it would make sense. It's possible. It's the same. You can really use it. Don't know.
What are the other strategies? What kind of strategies are we talking about?
I have not looked that deep into it. That's why I'm asking.
Yeah. So you have So the thing of the evaluation strategies in GHC is you can define on a list or tuple or data type, you want an abstract, an aggregate data type, to define how it needs to be evaluated when you want to fully evaluate it. And you can apply different strategies from outside and compose them, and how deep, if it is nested, how deep you want to look. And that's something you can, if you want to use this, you want to use it, if you want to use it practically, I think, but I don't see the. I haven't seen the
NF data in this case. NF data.
You need it. I don't think you need it for the strategies. For the strategies, you only need it if you use DeepSec, I think. And this is when you fully evaluate. When you do not do this, but use other strategies like R0, which doesn't anything, or Haskell, which does sequential, so weak normal form evaluation, then you don't need this. But this NF data, you can take it, switch the type, class, and instance declarations to Frege style and can use it.
Oh, okay.
Yeah, it's no problem.
So this could be some contribution of this. That would be great. My other question was there are actually in the there are benchmarking harnesses like, for example, JMH or something. Do you have considered using this one?
For this particular.
Okay. Would this be appropriate to fall under your cases? Because I mean, the problem is for me. You have you know that JVM benchmarking is hard. So everybody who comes from Java only will not be convinced when he sees two benchmark.
And so how I did it. It's not only the one function. I did warm up I did class loading phase and warm up phase, and then those. So
I have seen this, but still it's not convincing for someone who is not.
But for the speed up, it's totally convincing, I think. So
Yes, true. But then we should be able to get the same results with maybe a popular tool like JMH.
You get a bit different information for profiling and for finding hotspots in profiling and so on. But I would say for the in wall clock timing is always a little bit brittle with respect to what else is your computer doing. And so it may give you it gives you different results at a different grain of granularity, much more fine granular. But for an entry into the topic, wall clock timing is always convincing because it somehow relates to the user experience when using a service or something.
The question was if I would more in this direction.
Yeah.
But the first one is it's a marketing thing. For what I'm asking for. The first thing is to say, look, this is really convincing because we use a wide used tool.
Mm-hmm.
The second one is look, the message, this subkutan message, look, you can use Java tools, it's Frege, and so on and so on.
This is also interesting, yes. For that reason, yes, JMH would be interesting. When I'm actually using most of the time is Visual VM, just on the side, for memory and the CPU at the same time, and threads and so on. And we can use the your kit.
How to measure performance in Frege or something.
Yeah, you can do that. Yeah, that's true.
Just
it is more these kinds of tools on the Java side as a Java engineer. I use these kinds of tools if I have to pinpoint a certain, if I really have to profile, not for speed measurement, but for profiling, finding where is the hotspot. Actually, what could be even more interesting in that regard is a JIT watch. Let's say there's a command line tool for Java, and you run the Java code and you get information from what JIT is doing, and where it inlines things and so on. So that could be even more interesting. It's a bit difficult to interpret what it does, but you get lots of interesting information. So there's certainly lots of more engineering work that can be done in giving you more information where things could maybe even be optimized.
Yeah, it's nevertheless would be cool if we, let's say, we would find out how to do this, and then we could have some wiki entry where we write, you do it. If you want to do this, then
yes, correct.
It can be done or it cannot be done, maybe.
It can certainly be done because it's Java code. The question is how well you can interpret this. We can even use the JDB command line debugger with Frege.
Yeah, we can. Yeah, sure.
Yeah, sure.
Everybody uses it for just those measurements.
Yeah.
I mean, one point which speaks for JMH is that you try to take away all this JIT warm-up, because I mean, this is a very, I mean, the JVM is a complex machine, and they try to be just like, I mean, everything is warmed up, all classes are loaded, everything which can be inlined is inlined, and then you do the benchmarking. Because I mean, this is more level. I would say this is like micro benchmarking.
It is.
So, and then this is
nano
really,
benchmark.
Yeah, this is really, I mean, like.
But then, when it comes to benchmarking and comparing JVM languages, I've been there,
Yeah, sure.
And you can compare micro benchmarks, which usually do not apply at all to what you really want to know. And what you really want to know, not as a language implementer, but as application programmer, is how well will my application run when I program this in this language. And my current, and I would claim, my claim would be, also from these numbers, extrapolating from these numbers, if you program, and having implemented in Frege FX REPL, of course, it is, you will see no difference whatsoever. The user will not see any difference whatsoever, whether you write it in Java or Scala or Frege or Groovy. The user will not notice. You have so much other stuff that can go wrong.
Exactly.
And he will not notice in performance-wise. Anyway, we still want to optimize behind the covers. So and that's also already interesting. It's already an interesting statement to make. How much faster or slower are you? You say, under this consideration, we are one-to-one.
Exactly. I would say this is the most important thing, that you can have a functional programming language on the JVM, which is not slower than if you use pure Java. Because I mean, you're making a DB call or you're making a HTTP request, and then there's only performance.
And even just normal stuff. Even if you don't go to the database, even if you don't have remote calls, take the Java FX REPL. I mean, it's a pure desktop thing, and you don't you don't recognize anything beside that the REPL itself needs in the back talk to this other process and evaluate and then comes back. So the whole desktop application is not slower than the command line application. So that's the thing.
So it's a bit of a question where we want to go. We want to attract those number crunchers for Frege, then it would absolutely make sense for me to go this way. And if not, it would also make sense to go this way, but maybe not that much.
Possibly for us, for implementation optimization is always interesting.
And
yeah, you know, it's just so that people are obsessed by this number.
yes.
True. Yes. True.
Even if I dislike this, I have to take it into consideration.
Yeah, that's
why I did this a bit, but
that is true. Yeah.
Yeah, we should then. It should be then a comparison with other JVM languages and not GHC.
Yeah.
So, okay, we can.
Oh, whatever.
Yeah. Okay, we can discuss
I mean,
and yeah, it's.
Don't want to extend your activities
no.
infinitely, but if you could explore the possibilities of using this or that.
And also, there are many ways I can go now, because I haven't even covered the parallelism of Haskell fully, because no parmonad, no data flow variables. So there's much to the strategies. I could implement them for Frege. And
but
then
you leave all this besides and do the STM thing?
Yeah, that was my next point.
Yes, well,
we will do the STM.
So
I always wanted to do this. You know.
You always wanted to do this. Can I do that?
When I say I do it, I mean I let you do it.
I see.
This is how it works.
Okay. So tomorrow I have the first version.
Come on, it's only 3 functions.
It's 4. Yeah, 4 functions.
Yeah, I think it's not that big, but the testing is not big.
Once you have immutability, you're already there. Almost.
There's also a hash map try.
Hash map try. Since we have that, I'm so happy we have that. That was a feat, you know.
Okay.
I was just proposing this thing, and then like half a day later, I have it, you know.
It was half a month.
Yeah. What wasn't so much? Or it was you saying, look what I've done in the afternoon.
Okay. So
it was really cool.
When I am at it, I can.
Yeah.
So, any other questions so far? For the end, not so far.
Thank you so much.
Yeah. Thanks.